The only way to remember the pMOS saturation conditions is to know what the nMOS saturation conditions are and then inverse the sign of the inequality. And that's it. Very, very, very simply. You don't need to get confused with absolute values and things like that over here, only to remember these saturation conditions. So if VGS is more or equal than VTH in saturation of the nMOS, then for the pMOS, the opposite must be true. And also, by the way, we must also remember that all of these values here are negative, all right? For the nMOS, all of the values are positive, for the pMOS are negative. If VDS must be more or equal than VGS minus VTH for the saturation of the nMOS, then for the pMOS, VDS must be less or equal than VGS minus VTH. It's the exact same conditions, but keeping in mind that these values here are negative and that this sign here is inversed in relation to this sign over here. And that's it. We only need to remember this. Now this circuit is nothing but this circuit, all right? I put my transistor over here. I have my two batteries over here with a negative terminal connected all the way to the ground. The ground is nothing but a common terminal with 0 voltage. For the pMOS, the source is at the point with higher voltage over here. And we also note that the arrow points towards the MOSFET. This means that the current actually flows like this. Even though we draw the arrow from here all the way to here of the current. Why? Because the current, by definition, must flow into the drain, all right? And we will see later that the current has a negative value. All right, now we are asked to find how much is the W over L of this device so that this little device here is in saturation without and with channel length modulation. We are given a couple of values here, VTH minus 0.4. Again, these things are negative over here, right, for the pMOS device. And we are given the battery value here, and we are given the resistance value over here. Now for the saturation conditions, again, I will use these conditions here, the exact opposite of this. VGS must be less or equal than VTH. How much is VGS? Well, VGS is VG minus VS. So it is 1, all right, VG, 1, minus V minus S, VS. How much is VS? 1.8, all right, VDD. So all of this is less or equal than VTH. Yeah, it's less than VTH. On to the second condition, I'm putting this condition over here. So it is VDS is less or equal than VGS minus VTH. VDS, how much is VDS? I don't know yet, so I leave it like this. How much is VGS? Well, I found it earlier, all right? 1 minus 1.8, it says minus 0.8. How much is VTH? 0.4, all right, minus 0.4. So it's 0.8 minus 0.8 plus 0.4 minus 0.4 over here. Now, I have named this loop over here as loop 1. And so I can now do what's known as a KVL on this loop. I will do this KVL. Why? Because I want a relationship between this voltage here, VDS, and something else in the system that I know how to measure. So it has to be, let's say it from the beginning. The current flows like this. The loop goes like this. So the loop and the current go to the same direction. All right. Now, when we have a current flowing from here to here, since it is at the same direction as the loop, then we put a positive sign here and say that the voltage from to the resistor here it's ID or at times RD from the Ohm's law. Then we enter again a positive terminal here, DS, right? If we call this SD, which is very common for pMOS Some electronics books call these values with the opposite sign. All right, they call this SD. Don't worry about it. We will put a negative sign. Now we enter the positive sign here, VDS. All right, and then we enter again a positive terminal here on the VDD, so it is plus VDD. And all of this must be equal to 0. Now, thanks to the VDS I have found previously from my saturation conditions, I replace all values here carefully, all right? And given the RD here, but it's kilo ohms, so it is 2 times 10 to the power of 3. VDS is minus 0.4, VDD is 1.8, and if I do the math here, ID is this. It has to be this. Again, notice the sign is negative. So again, what we talked about in the beginning, the current must flow like this, even though we draw it like this. Now from theory, we know that the current of the MOSFET in saturation must be 1/2 mu p Cox WRL VGS minus VTH squared. And because we have a pMOS device instead of an nMOS, there is a minus sign here again, that the current flows in a different direction. Replacing all these values over here, all right, we know everything from here. We know VGS, we know VTH, we know the current from here, all right. We replace everything, and we are left with W over L, the one I asked from in the beginning. And if I do the math, W over L is 87.5. In the normal range of the design details of the MOSFET, it's very common to go with a W over L of about 100, all right, in these devices. And so we found the W over L for lambda equals to 0. Now for the case where we have channel length modulation, we do pretty much the same analysis over here until up until the KVL, alright, nothing real changes over here. The only thing that changes when we have channel length modulation is the current equation, alright, from theory. It's pretty much the same, but we also add this term here, 1 minus lambda VDS, minus. For the nMOS device, it's plus. For the pMOS, is minus. Why? Because this VDS is negative, all right? And we can't really define a negative lambda because it will not have a physical meaning that made sense if the lambda was negative. So we just put a negative sign over here and do pretty much the same as we would do normally, all right? Now, thankfully, the exercise gives us this voltage and this voltage, these resistors, so we don't need to do something very complex here. We just replace all of the values we have found previously, all right? And now, again, we solve in respect to W over L, and we get that the W over L is slightly lower here than it was previously, all right? So in our saturation, when we put the same voltages over here and over here with the same resistor, it turns out that when we take into account channel length modulation, W over L is slightly, the dimensions are slightly closer to each other, perhaps a bit easier to make, all right? Perhaps a bit cheaper to make, like this, than this. Taking into account channel length modulation made our lives a bit more complex, all right? We had an extra term over here, and in this instance, it was kind of easy to find the W over L suitable here. But there are many times where this term makes things much more complex and much more difficult. So we see that there is a difference here in the W over L, but is it that big of a difference? Well, it depends on the overall context of the circuit and what we want to achieve. So sometimes we take this into account, sometimes we don't. For exercises, If we are giving exams in electronics 1 or 2, our exercise is going to tell us, all right, it's going to tell us if we need or if we don't need to take into account channel length modulation. And that's it. That's it, how we basically solve MOSFET exercises that are of the pMOS MOSFET, all right, not of the nMOS. So it's pretty much the same analysis. Some things that we need to remember, all right? There are a few things that we need to remember and forget. And we, in the saturation conditions, all we need to do is just inverse the signs, all right? Basically, that's it. All right, check out the MOSFET playlist for more MOSFET tutorials and electronics videos on this channel. Study well and take care.